Section 17.3 Applications of second-order differential equations. Consider the motion of an object with mass m at the end of a spring that is either vertical, as in the first figure, or horizontal on a level surface, as in the second figure. Then Hooke's law says that if the spring is stretched or compressed x units from its natural length, then it exerts a force that is proportional to x, a restoring force equal to negative kx, where k is a positive constant called the spring constant. If we ignore any external resisting forces due to air resistance or friction, then by Newton's second law, force equals mass times acceleration, we have m times the second derivative of x with respect to t equal to negative kx, which we can set equal to 0 by just adding kx to both sides, and we end up with a second-order linear differential equation. In fact, it's even homogeneous because it equals 0. Its auxiliary equation is m times r squared plus k equals 0 with roots plus or minus omega I, where omega is the square root of k over m. So you could just use the quadratic formula for that. And then our general solution must be x of t equals c1 times the cosine of omega t plus c2 times the sine of omega t. We can also write this, though, as x of t equals a times the cosine of omega t plus delta, where omega is the square root of k over m, a is equal to the square root of c1 squared plus c2 squared, and cosine of delta is c1 over a, but sine of delta is negative c2 over a. And we call this type of motion simple harmonic motion. So let's just quickly understand why we can rewrite it. If we were to set this equal to a times cosine of omega t times c1 over a plus sine of omega t times c2 over a, then all we've done is multiply on the outside by a and divide on the inside by a. So we just multiplied and divided by the same number, so all we did was multiply by 1. We didn't change anything. So what we could then do is write a times the cosine of omega t times, well, c1 over a is cosine delta by what we're saying, so this would be cosine delta in here, plus sine of omega t times negative sine of delta, so I just put a minus over there, so minus sine omega t times the sine of delta. Well, in this case, we have cosine, cosine minus sine, sine, two different things, omega t and delta, omega t and delta. So we can use the cosine angle addition formula. And when we do that, we just get cosine of omega t plus delta. So we have a couple different names for these different things. Omega is the frequency. A is the amplitude. And delta is the phase angle. So let's do an example of this. A spring with a mass of 2 kilograms has natural length 0.5 meters. A force of 25.6 newtons is required to maintain it stretched to a length of 0.7 meters. If the spring is stretched to a length of 0.7 meters and then released with initial velocity 0, let's find the position of the mass at any time t. So how about we first use Hooke's law? So according to Hooke's law, we have k times how much we stretched. Let's see, we're going from a natural length of 0.5 to a stretched length of 0.7, so that means we stretched by 0.2. So we'll take k times 0.2, and that must equal our force of 25.6 newtons. So that allows us to solve for k. We get that k is equal to 25.6 divided by 0.2, which is 128. So now we also know that m is equal to 2 because we were told the mass is 2 kilograms. So we can plug that in and get our differential equation. So that's 2 times the second derivative of x with respect to t plus 128x equals 0. We also have that omega is equal to the square root of k over m, so that's 128 over 2, so that's 64, so that's 8, square root of 64. And this means that we can write our solution x of t as c1 times cosine of omega t, so that'll be cosine of 8t, plus c2 times the sine of 8t. And we also know that our initial length we are stretched to is 0.7. So that means we are initially stretched by 0.2 meters. So that means that x of 0, and if we plug in 0 for this, we get this is 0, and this is just going to be c1. So we get x is 0, c1. That must be how much we initially stretch by, which is 0.2. So we know what c1 is. If we want c2, we can take the derivative, x prime of t, and that's equal to negative 8 times c1 times the sine of 8t plus 8 times c2 times the cosine of 8t. So our initial velocity is 0. So that means that x prime of 0 must be 0. But if we plug in 0 over here, this is 0. We just get 8 times c2 is 0. So that's the same thing as saying that c2 is equal to 0. So we have our position of the mass at any time t given by x of t equals 0.2 cosine 8t, because this ended up being 0. Very often our differential equations in these situations become a little bit more complicated because of external forces, such as a damping force, which is a force like when a spring is submerged in a liquid, or in reality like a shock absorber on a bicycle. So a damping force affects our differential equation a little bit, and we're going to assume that it's proportional to the velocity of the mass and acts in the direction opposite to the motion. And this can be sort of experimentally determined, but of course we're not going to do that. So we have our damping force equal to negative c times dx dt, where c is a positive constant called the damping constant. So then Newton's second law gives m times the second derivative of x with respect to t equal to the restoring force plus the damping force. So that's negative kx plus negative c times dx dt. So that means that when we move everything over to one side and set it equal to 0, we end up with still a homogeneous differential equation, but it's just slightly more complicated. So now it has auxiliary equation mr squared plus cr plus k equals 0, so its roots become a little bit more complicated using the quadratic formula. So we end up with a couple different cases. Our first case is that if we have the discriminant c squared minus form k greater than 0, then we have overdamping. So in this case, we have R1 and R2 as distinct real roots, so our solution to our differential equation is given as we would expect, with C1 e to each of those roots, C2 e to the other root, and it looks something like this in this picture, where the shock absorber, you can imagine, or damping force, whatever you want to think of it as, is preventing this thing from oscillating. It can only really cross the axis one time. Whereas if we have underdamping, then we have the discriminant negative, and notice it oscillates tons because we didn't dampen enough, so we didn't absorb the shock. So in that case, we have roots given by complex numbers, and our solution is given, as would expect, e to the alpha t times c1 cosine beta t plus c2 sine beta t, where alpha is negative c over 2m and beta is omega. But the last case, or the middle case, however you want to think about it, where we have critical damping, is pretty similar to overdamping. We just end up with one real root, we throw in a t like we threw in x, and we get our solution, and it looks similar to when we had overdamping. So this is basically just when you damp like exactly enough. You should absorb exactly enough shock, you could think of it as. So the two main differences in the pictures are with overdamping and underdamping. Suppose that the spring of example 1 is immersed in a fluid with damping constant c equals 40. Let's find the position of the mass at any time t if it starts from the equilibrium position and is given a push to start it with an initial velocity of 0.6 meters per second. So from example 1, we have the mass is 2, and our constant k is 128. So we have the differential equation 2 times the second derivative of x with respect to t plus, in this case, 40, because that's our constant c, times dx dt, our damping constant c, plus 128x equals 0. So we can divide by 2 and get that this is d squared x dt squared plus 20 dx dt plus 64x equals 0. And this thing will have auxiliary equation r squared plus 20r plus 64, which we can factor as r plus 4 times r plus 16 equals 0. And solving for those roots, we get r is -4 and the other root is -16. So those are both real roots, so that means that our equation x of t can be written as c1 times e to the first root -4t plus c2 e to the -16t. And notice we also have x of 0. We saw that that's equal to 0. So plugging that in, we get c1 plus c2 must be equal to 0, because they said that it starts from the equilibrium position, so x of 0 must be 0. Okay, how about we also take the derivative, because they told us what the initial velocity was. So our derivative is -4 times c1 e to the -4t minus 16 times c2 e to the -16t. And that means we plug in 0, and we get -4 times c1 minus 16 times c2, which is our initial velocity of 0.6. Okay, so that means that by this equation, we have c2 equal to -c1. So how about I plug that into this equation over here, replace c2, I'll get 12 times c1 is equal to 0.6. So that means that c1 is equal to 0.05. So we plug that into our equation for x of t, and we can factor out the 0.05, so we get x is equal to 0.05 times e to the -4t minus e to the -16t. This is not the only possible force, though, that we could end up having. We could also have some other external force, f of t, and then Newton's second law would give that m times the second derivative of x with respect to t would be equal to the restoring force plus the damping force plus that external force. So then instead of having a homogeneous equation, the motion of our spring would now be governed by a non-homogeneous differential equation that equals f of t instead of equaling 0. We're not going to do an example of that, but we'll do another example of application of a non-homogeneous differential equation. So let's consider the circuit shown in the figure. It contains an electromotive force E supplied by a battery or generator, a resistor R, an indicator L, and a capacitor C in series. If the charge on the capacitor at time t is Q equals Q of t, and the current is the rate of charge of Q with respect to T. I equals the derivative of Q with respect to T. It is known from physics that the voltage drops across the resistor, inductor, and capacitor are Ri, L times di dt, and Q over C, respectively. Kirchhoff's voltage law says that the sum of these voltage drops is equal to the supply voltage. So we end up with a differential equation. But then we also have that our current, our rate of change of Q with respect to T, is I, so we replace that with our derivative. If we're taking the derivative of a derivative, that's a second derivative, and then this is just the derivative, and then we have Q over C, so it's the same as 1 over C times Q, so this is a linear differential equation in terms of Q. And notice that it's not homogeneous because it equals E of T, our electromotive force. So if the charge Q0 and the current I0 are known at time t, then we have initial conditions. Q of 0 equals Q0, and I of 0 is the derivative of Q of 0, and that's I of 0. If we want, we can also get a differential equation with respect to, by differentiating with respect to t for the current. So we can have everything in terms of I instead of in terms of Q, and all we do is just differentiate our differential equation in terms of charge. So instead of equaling E, we equal E prime. As an example, how about we find the charge and current at time t in the circuit of the figure if R is 40 ohms, L is 1 Henry, C is 16 times 10 to the negative 4th farads, and E of t is 100 cosine 10t, and the initial charge and current are both 0. So let's write our differential equation first. We have the second derivative of Q with respect to t plus 40 times dq dt plus 625q must be equal to 100 times the cosine of 10t. Okay, so this thing has auxiliary equation r squared plus 40r plus 625 equals 0. So solving for our roots, we get, using the quadratic formula, r is equal to negative 40 plus or minus the square root of negative 900 over 2. And that's negative 20 plus or minus 15i. So this means that our solution to our complementary equation is equal to e to the negative 20t, because that's alpha, times c1 cosine beta t, so that's cosine 15t, plus c2 times the sine of 15t. And we need now a particular solution, then we can combine those and we'll be able to solve our non-homogeneous linear differential equation. So for a particular solution, how about qp of t equals, well, this thing is equal to cosine, so we'll just take a more general version of cosine. So we'll have a cosine 10t, and we'll add that to b times sine of 10t. We'll use the method of undetermined coefficients. So we will figure out what a and b are. We'll take the derivative, so we can get qp prime is equal to negative 10a sine 10t plus 10b cosine 10t, and we get that the second derivative qp double prime is equal to negative 100 a cosine 10t minus 100b sine 10t. Okay, so how about we take these and we'll plug them into our differential equation. So this will be a little bit messy, but we can do it. So we'll take our second derivative, because that's what goes first. So we'll write that first, minus 100 A cosine 10t minus 100 b sine 10t plus 40 times minus 10a sine 10t plus 10b cosine 10t plus 625 times a cosine 10t plus b sine 10t, and that should equal 100 times the cosine of 10t. Barely fit. So what I did was I took this second derivative, threw it into the second derivative. I took 40 times the first derivative, so 40 times that, and then 625 times our particular solution Q, and that should equal 100 cosine 10t. Okay, so notice that we have to match up our coefficients, so how about we try simplifying this a little bit. We can group together all of our cosines and sines. So if we do that, we'll get 525a plus 400b times the cosine of 10t plus negative 400a plus 525b times the sine of 10t equals 100 cosine 10t. And notice that we have no sines on this side, so this must be 0. And we only have 100 cosines on that side, so this must be 100. So we can write that out. We'll set 525a plus 400b equal to 100, and we'll set negative 400a plus 525b equal to 0. So solving for a and b, well, first we could, how about just simplify over here by dividing by 25. So we get 21a plus 16b equals 4. And then we can divide the other one also by 25. We get negative 16a plus 21b equals 0. So that means that we can solve this system for a and b. We'll get that a is equal to 84 over 697. And we'll get that b is equal to 64 over 697. So we'll plug that back into our particular solution, QP. So now we know what it is. We see that QP of t is equal to 1 over 697 times 84 cosine 10t plus 64 times the sine of 10t. So that means that our solution, our general solution, Q of t, is equal to our complementary equation solution, QC, plus our particular solution, QP. So that's equal to e to the minus 20t times C1 cosine 15t plus C2 sine 15t plus 4 over 697, because I'm factoring out 4 there, times 21 cosine 10t plus 16 times the sine of 10t. And we're given that the, let's see, initial charge and current are both 0. So that means that Q and its derivative are both initially 0. So how about I look for what Q of 0 is? I could solve for my coefficient C1 in the initial value problem. So q of 0, if we plug in, is just going to be c1, because this is 0, plus 84 over 697, because this is 0. So that's supposed to be 0 if the initial charge is 0. So that means that C1 must be equal to negative 84 over 697. So now let's look at our current equation. So that's I, which is the derivative of charge, so dq dt. And that's going to be e to the minus 20t times negative 20 times c1 plus 15 times c2 times the cosine of 15 plus negative 15 c1 minus 20 c2 times the sine of 15t plus 40 over 697 times negative 21 sine 10t plus 16 times the cosine of 10t. And we have our initial current is also 0, so we know plug in I of 0, we'll get negative 20 times c1 plus 15 times c2 plus 640 over 697. That must be equal to 0. So solving for c2, we get that c2 is negative 464 over 2091. And now that we know what both of our coefficients are, we can just plug in. We'll see that q of t is equal to 4 over 697 times e to the minus 20t over 3 times negative 63 cosine 15t minus 116 sine 15t plus 21 cosine 10t plus 16 sine 10t. And our current, we can plug in for that too. We get 1 over 2091 times e to the minus 20t times 1920 cosine 15t plus 13,060 sine 15t plus 120 times negative 21 sine 10t plus 16 cosine 10t.